Hello, everyone. Welcome back. Today, I'm going to be talking about polynomial functions in factored form. Last day, we talked about just some general rules about polynomials, but we're going to actually be able to graph them when we have factored form. So any polynomial can be written in this form with a some coefficient, and then times, x minus alpha, x minus beta, x minus that one, and x minus psi, I think, is said to be in factored form, where a is our leading coefficient, and then all of these are x-intercepts or zeros. So this is very similar to quadratics with zeros, except with quadratics, we can only have two zeros or one zero or none, right? Um, and so when we have quadratics in factored form, it's very easy to tell where the zeros are, and so we can easily plot them. And there's quite a few things we can tell about that. Now, for today, we're just going to practice sketching with polynomials already in factored form, but in the future, I will also talk about how we can actually go from the standard form to factored form. So, what steps we would have to take to factor it. Luckily, once we get it down to just having, quadratic, we know how, right? We already know how to solve quadratics and how to factor quadratics. But when it comes to a degree 3 polynomial, there's only select ones we know how to do, and that we can actually do with quadratic technique. Same with degree 4, degree 5, degree 6, and so on. There's very few of those we can actually factor without learning new techniques. So we will learn new techniques soon, but for today, we're just going to learn to sketch with already done ones, with ones that are already factored. So here it says to sketch the graph of this polynomial. So what do we know? What do we know? Well, we know that well, we know what? We know that the zeros or x-intercepts are, let's see, 4, 0, 1, 0, and negative 3, 0, right? We know that from the zero product property, in that if any of these things that we're multiplying together are 0, the whole thing is 0, and therefore it's an x-intercept. So this is very much the same as what we would do for quadratics. So now I'm going to draw those points. Let's draw them. We have 4, 0, 1, 0, and negative 3, 0, like that. Okay, now let's go to y-intercept. Well, what is our y-intercept? Our y-intercept would be the same as f of 0, which is minus negative 4, negative 1, 3, which is negative 12. So therefore, 0, 12 is our y-intercept. So it looks like we don't have enough space to do that, actually. So I'm going to label this part of the graph. Let's see this as 4, 8, 12, 16, and now I can draw this here. And then I'll label these parts of the graph too, actually, as well. I should do that in a moment, just for good formatting, to always label our graphs. Even though I guess it's kind of sometimes just assumed that with one unit, it's just meaning one, but these are different. So I'm gonna label them. 1, 2, 3, 4, 5. Okay, good enough. Awesome. Okay. So what's the leading coefficient? Well, the leading coefficient is negative 1, which means it is negative. So because our leading coefficient is negative, or less than 0, what do we know about that? We know that it follows the same pattern as a negative sloped line, right? Because this is an odd degree function. And so we know that as x approaches infinity, that y approaches negative infinity. So here I'm going to draw a line going downwards forever. And then up here I'm going to draw a line going upwards forever. Because as x approaches negative infinity, y approaches infinity, right? We know that because we know that there's a negative leading coefficient, and we know that the degree of this polynomial is degree 3, right? There's 3 x values here. There's 3x. So if we were to expand this, we would get x cubed as our biggest exponent, right? So if you're confused by how we know that based on the leading coefficient, make sure to review the previous lesson as we go into detail about end behavior there. Okay. All right, so let's go ahead and fill the rest of this in. Because in terms of where the turning points are, we actually don't know that. The only way to find the turning points algebraically, that I know of anyway, is, one second. This should be negative 12, not positive 12, my apologies, is using calculus methods. So we can use calculus methods in order to figure out the turning points. However, in this course, all I expect from you when I ask you to sketch a graph is to include all the zeros, include correct end behavior, and include the y-intercept. Those are the three things that we know how to include. So when I'm marking a graph and how well you did drawing your graph, those are the things I'm going to be looking for. I'm not going to look to see if the turning points are going to be correct because, let's be honest, they're most likely not going to be correct because we don't know how to actually find them yet. And that's not something we'll learn until the calculus course. Now, once you get to the calculus course and we're doing curve sketching, then I also expect the concavity to be correct, and I also expect the turning points to be correct. So I expect a couple extra things, but those are not things we're going to learn in this course. So for this course, this would get a full check mark. In the calculus and vectors course, this would not get a full check mark because it doesn't actually have the correct turning points. I just kind of guessed, right? So there we go. So long story short, as long as for this course, as long as your graph has the correct x-intercepts, the correct y-intercept, the correct end behavior, you're good. That's the most important part. Okay. Very, very good. Let's move on. Let's move on to example 2. Here it says, find the equation of the function below, given that f of 1 is 7.2. So basically what they're saying is this point here, it's at 7.2 with respect to y. So how can we find the equation of this? Well, let's think about it. What can we tell about this equation? Well, I can tell that there are 3 turning points, and so the maximum degree of this would be, the minimum degree of this, it would have to be at least degree 4, so it likely is degree 4. I can also see that there's zeros at -2, -1, 4, and 5, right? So I can see that there's x-intercepts at the following points, at -2, -1, and 4 and 5, right? And what else can I see? I can see that this function opens up on both sides, so it must be an even degreed function. So given that there are 4 zeros and 3 turning points, I'd say it's a pretty safe bet to say this is a degree 4 polynomial. Okay, so this is degree 4 polynomial. And to make our equation, we just need to do it in factored form. The equation is going to be a times x plus 2, x plus 1, x minus 4, and x minus 5, right? How did I come up with those numbers? I used my x-intercepts in order to know those numbers. Very good. Okay, so the only thing that's left here is I don't have the a value. It's required that I fill in the a value in order to get the correct answer here for my equation. But we do have a point. We know that f of 1 is equal to 7.2. So if I sub in 7.2 for f of x, and I sub in 1 for all my x values, then what do I get? Let's see what I get. That would be 7.2 equals a times 3, 2, -3, -4, which means 72a equals 7.2, which means a equals 0.1. So that means that therefore my overall equation is going to be f of x equals 0.1, x plus 2, x plus 1, x minus 4, x minus 5. And there we go. So let's review quick. What did we do for this one? We wrote down the x-intercepts. we also knew a point. And so we were able to plug in the x-intercepts into those Greek letters that we saw at the top. And then we were able to use the point and the fact that we had all the intercepts to find, or all the x-intercepts to figure out what the a value was. And then we were good to go, because all the things we really need to do to write the equation of a polynomial in factored form is we need the a value, which we found, and we need the x-intercepts, which we were able to locate on our graph. Very good. Okay. Now it says, write the equation of the function with x-intercepts 2, 4, -1, -3 that goes through the point 0, -60. Okay, so let's do that. What do we know about this function, the function already, the equation of it? We know that f of x is a times x minus 2, x minus 4, x plus 1, x plus 3. We know that. Now what we need to do is we need to plug in 0 for x and -60 for y. And that will get us to find the a value. And then that means that we have 24a is equal to -60, which means that a would be -2.5. So now that we found that, we have found the equation. So therefore, our equation is f of x equals -2.5 times x minus 2, x minus 4, x plus 1, and x plus 3. So there we go. Awesome, we did it. Then it says to sketch the function. So now that we have the equation, we're able to sketch here. So let's see, what are our zeros first of all? They are 2 and 4 and -1 and -3. So there they are. We also know that the end behavior, it's going to open down on both sides and go like this because our leading coefficient is negative, and this is a degree 4 polynomial. And what else? We know that it goes through the point 0, 60. So we've got to use that. Or sorry, 0, -60. 0, -60. Okay, so we've got to use that fact. So if we got to get to -60, let's say this is -33 down and this is -60. And we'll say that point is there. And then as for, let's make the scale accurate at least, 30, 60. There we go. And then as for the points up here, they don't actually, so these points all need to be accurate, right? Because that's our intercept. But the turning points up here don't have to be accurate. We can just draw something random there. Well, not something random, but we can just kind of draw them as we would assume them. And we're good. Because again, I don't expect the turning points, I don't expect to be correct at this stage, because I haven't taught you how to do that yet. And I won't do so until calculus and vectors. Okay, so there we go. There it is. All right, I guess the one last thing I should do is label my graph. So I will do that. 2, 3, 4, 5, -1, -2, -3, -4, -5. And there we go. All right, well, that is everything for today. Good work today, everyone. And I will see everybody back for next day. Bye, everyone.